So welcome everyone. Today we will talk about the scattering theory. We'll just form the basis of the scattering theory so that we can take this forward in the next classes. The basics of the scattering theory would be covered, but there are a lot of things that we need to cover, especially on the mathematical part that will be covered on later on. So we'll just give a flavor of what is a scattering theory today, and then we'll build upon this in the coming up sessions. Okay, so now when you talk about our hand, when I shine a light on my hand, so there are many tissue constituents responsible for scattering of light, right? So both for absorption and scattering. In this session, we'll mainly focus on scattering. So what are the different tissue constituents? Here there are like cells, there are water molecules, there are lipids, collagen, hemoglobin, and other tissue constituents. So they part of it actually absorbs, and part of it also scatters the light on different directions. Now each of these particle can be considered as each of these components can be actually considered as a particle, right? So when you consider this as a particle, there could be when we are shining the light on that particle, there could be light in different directions. So you have the light which is propagating in forward direction. Okay, so here you can see that you are shining the light from this side, okay, from left to right. This is the incident light source, and most of them is kind of propagating in the forward direction, that is towards the right hand side. But because of this particle which is kind of scattering over here, this is the scattering particle. Because of this particle which is scattering, some of them is getting back scattered. Okay, so when you talk about scattering, it is constituted into two parts. One is forward scattering, another is back scattering. Now to define the scattering, there is one more simpler parameters that you can use to define scattering for different tissue constituents corresponding to different diameter of the size of the particle, right? So that one of the particle which is important is known as the scattering size. Okay, size of the scattering particle. Here you can see that it is defined using x, and x is nothing but equal to 2 pi r by lambda. Now r is the dimension of the particle, scattering particle, and lambda is the wavelength of the light which is incident on this scattering particle. Now what is going to happen over here, if you see it carefully, r has a units of centimeter, and lambda has also unit of nanometers. So, but both have in order of meters, right? So both will get cancelled, and what you eventually get is a unitless. So this size of the scattering particle is a unitless parameter. Now based upon the value of this x, you can actually classify the type of scattering as Rayleigh, Mie, or geometric. What we have seen is that, especially from this lecture notes from Simon, Professor Simon A. Khan, you can actually plot the phase function. Now we will talk about this at a later stage in more details of how you can actually get these phase functions. But let us assume that you have calculated your size of the scattering particle, and that that value is kind of very high, right? So that high value of size of a scattering particle signifies that it will have more scattering in a forward direction, and lower the value of the size of the scattering particle, it will actually have the forward scattering would be getting lower, and then it will almost be kind of an isotropic, right? So when you see the size of scattering particle to be very high, as you can see over here. When it is very high, it's known as a geometrical scattering. When it is approximately equal to 1, as you can see over here, it's approximately equal to 1, then it is kind of Mie scattering, and if it's like very less, then it is known as a Rayleigh scattering. Now this is directly correlated with the dimension of the particle, right? Now if the dimension of the particle is like very large, then you will see this as a forward scattering. If the dimension is almost equal to the wavelength of your incident light beam, it's going to be kind of Mie, and if kind of very less dimension, then it's kind of it will be in the Rayleigh regime, right? Now there is one more. So we will talk about many different parameters that is used to define the scattering. One of them is the size of the scattering particle, as I discussed over here. One more is known as an anisotropy factor. Now what is anisotropy factor? Now I want to know how much is my forward scattering going to happen, right? So this parameter actually tells you the measure of the forward scattering that is going to occur, right? Now for example, if you see this is a particle, okay, this is the particle over here. Now when I shine a light source, maybe it's an electromagnetic plane wave which is shining on this particle, and I see light which is forward scattered, right? So scattering phase function is like only in the forward direction. In that case, the value of G, that is the anisotropy factor, would be equal to 1, is equal to exactly equal to 1. That is for a perfectly forward scattering particle. Now in the case where the particle is over here and I shine my light source from top to bottom and I get a perfectly backscattered light. So if here you can see that this is the phase function of a backscattered light source, and that is eventually for value of G equal to -1. So this is an example of backward scattering. When you see a particle over here and you shine the light source from the top to bottom and you see the scattering phase function to be a kind of an isotropic, like kind of a circle, it's uniform in all the direction, then the value of G is kind of equal to 0. Then it's isotropic scattering, right? So you can move from forward scattering to back scattering to isotropic scattering based on the value of G. Now as we are talking about tissue optics, the value of G is more or less equal to, or like it's kind of more than 0.85 and less than 0.95. So usually the value of G is given as around 0.8 value over here, and you can actually see that if you give a value of 0.8, then it would be like more or less you will see a forward scattering and some part of the light is being backward scattered, right? So now here you can see that the size parameter acts as a function of the anisotropy G in the y-axis, right? So here you can see that as the size parameter increases, that the dimension of a particle kind of increases, you can actually you can see that the anisotropy also kind of increases and it becomes saturated after a particular level. So if you want to learn about more about this Mie scattering, Rayleigh scattering, and how you can actually model this 2D models using COMSO multiphysics, you are encouraged to see the video over here. So we have recorded one video where we have done this scattering physics, scattering phase function, how to plot the scattering phase function based upon the diameter of particle, which is far less than the operating wavelength, approximately equal to operating wavelength, or far more than the operating wavelength, right? So you can build one model, you can do a numerical simulation using COMSO multiphysics, and you can see the scattering phase functions and how it is being plotted in this particular video, especially from that a part of the video which starts from 1 hour 13 minutes onward. Now in the earlier class we have talked about scattering efficiency. So when we were talking about the bulk properties of the tissue, we were talking about the bulk optical properties, that is scattering coefficient as well as absorption coefficient. When we talk about scattering coefficient, we talk about scattering cross section. So when we talk about scattering cross section, we talk about effective scattering cross section, right? So at that time we told that we introduced a parameter known as scattering efficiency, right? So from scattering efficiency we can actually quantify the scattering cross section, and from that we can actually quantify the scattering coefficient, right, of which is the bulk optical properties of your tissue. Now how do we actually calculate this scattering efficiency for different theory? So the first one is with the Rayleigh theory, right? So now with Rayleigh theory we consider the particle, again we talk about a single particle theory in this case. In that we talk about how do we move from multi-particle theory to single particle theory, and then from a single particle theory to multiple particle theory. So in this case we assume for a single particle again, and then which is surrounded by a media. So this NP is the refractive index of your dielectric particle, and M is the refractive index of the surrounding media. And it's kind of defined over here, so you don't need to work much about this one. So it's kind of defined. So QE is the scattering efficiency is given as scattering cross section, effective scattering cross section over the area, that is geometrical cross section, that is pi r square. So this is what we have already defined in our earlier session, right? And this you can actually this you can use it forward, and you can find what is the scattering cross section using scattering this particular formula. So x is nothing but the size parameter. This is an analytical approach of finding the scattering cross section, and r is nothing but the ratio of the refractive index of the particle over the refractive index of the surrounding media. R is the radius of the particle. So if you use this, you can actually find the scattering cross section, and from there you can actually find the scattering efficiency. Now what is important to see over here is that the size parameter x, and that actually is a function of power of 4. Okay, this so actually the scattering efficiency is a function of the scattering size with the power of 4, and it's inversely proportional to the wavelength with the power of 4. So that's how we actually can correlate with other. We were talking before about the scattering, why the light of coming from the sky is blue in color, right? So that's what is one of the reason that higher wavelengths they scatter more, they have more. So higher the wavelength, you have lower scattering efficiency, right? Lower the wavelength, higher scattering efficiency. So lower wavelength will go for higher scattering, and that's why blue, which is having lower wavelength, will have higher scattering, and that is the reason why you see the sky to be blue in color as compared to the other regions, right? So this is where it actually is coming through, right? Okay, so now one approach, as I discussed, is Rayleigh scattering. Another approach is Mie scattering. Mie scattering uses Maxwell's equations and Bessel's equation to find what is the scattering cross section. So again, you don't need to, there is a whole derivation about it, so I'm just trying to conclude that derivation and try to finding from that equation from where we can go, try to find out some kind of inferences from that equation. Okay, so here you have the zeta and xi, which are the Riccati-Bessel functions, and this you can actually use to find the scattering cross section, effective scattering cross section, as you have defined, that is scattering power divided by incident intensity of the light beam, and from there you can actually find what is the scattering efficiency over here. Okay, and over here again x is the size of the parameter, which is nothing but equal to 2 pi r by lambda, and r, which is nothing but the ratio of refractive index of the particle over the refractive index of the media, and r is the radius of the particle, right? So this is how you can actually define the QE for both Rayleigh scattering and Mie scattering. Now if you try to plot this the scattering as a function of size parameter, because both of them you will see that it is having a function as size parameter, it's both of these theory are having a function of x, which is size of the scattering particle. You can see that for very lower dimension, that is for a very lower size parameter till like 0 to 1, you can see that Rayleigh scattering and Rayleigh theory as well as Mie theory overlap with each other, especially in the linear regime, right? And this is where you can actually use the Rayleigh theory, because that is kind of, as you can also see over here, it's kind of very simple theories. You can easily find out what is the scattering efficiency and hence the scattering properties out of it, right? So for a very small dimension of particles, very small size parameters, you can use Rayleigh theory. But as you go on more than one, the size parameter more than one, here the Mie theory is kind of more accurate. And even though the mathematical the mathematics is more involved, but the Rayleigh theory does not actually catch up with the more accurate Mie theory. So Mie theory is kind of more accurate. When you talk about solving the same thing in COMSO multiphysics, you actually use the Maxwell's equation to find out the scattering phase function and then the scattering cross section. And so that's what you actually use the Mie theory. You actually work with the Mie theory and you get the without actually solving the Riccati-Bessel's equation functions and all those complicated equations, you can easily get what is proposed using the Mie theory, right? So why there is a more complete mathematical treatment? It actually works for isotropic dielectric spheres and cylinder. It can work for spheres of all size and refractive indexes and under illumination from any wavelength, right? So it's kind of more complete in the sense of how it goes with the relation with finding the accuracy. Okay, now let us try to find the scattering efficiency as a function of wavelength, as you can see, and as a function of dimension of the particle as well, right? So what you see over here is that for a very small particle, here if you see that this is the very small particle which is given as 0.02 micrometer, which is nothing but around 20 nanometers. The scattering efficiency is like almost like zero. So there is no scattering that is present because of such a small particle. Now when your particle becomes because this is around 20 nanometers. Okay, so if you carefully see that this is 20 nanometer and the x-axis starts from 200 nanometers to around 1000 nanometers, right? Now we have 0.2 micrometers, right? So now we are moving into around the regime of our operating wavelength. So it's around 200 nanometers. So it's somewhere over here, right? So this is the dimension of the particle. Okay, so we have a particle 200 nanometers and we are shining the light source like this one. Okay, and we are trying to find out what is the scattering efficiency, right? So here you can see that in this case there is significant scattering coefficient, but it kind of scattering efficiency, but this kind of reduces as the wavelength increases, right? Now when we talk about 2 micrometers, so it's around 2000 nanometers, and in that case it kind of saturates to a value of 2, and it's kind of fluctuating as you can see over here. And then if you increase this to 20 micrometer dimension, it almost kind of it reduces this ripple almost, and then it almost saturates to a value of 2 or so. Okay. So based on the different dimension of the particles, we can actually see that the scattering coefficient is kind of different. Now where are we going to use this kind of theory, right? So one of the application of this is a flow cytometry. This is a figure given from Wikipedia, and what they do over here is that they give the samples one cell at a time. So they kind of flow one cell at a time, and this is also used in blood sample analysis. So the blood that is drawn, it goes into this flow cytometry and try to understand the properties of the dimension of each particle. That will come in some time. So you shine a laser from here and it interacts with a single particle because we try to do so, and then because of the scattering it scatters in a particular angle. Now if it is more scattering angle, lower scattering angle, based upon that we can actually choose the the angle, and from there we can actually tell what is the dimension of the particles. We can back correlate to the dimension of the particle, right, based upon how much is the scattering going to occur. Now if you see this if you see the blood tissue constituents, you have many properties like many constituents like thrombocytes, erythrocytes, neutrophil, eosinophils, and all of them have different size parameters, right? Now you can use this size parameter and then you can correlate. So it's nicely demonstrated by in the book by Caroline, that this is an example of a density plot which shows the scattering of different properties of different tissue constituent, and this is the case of a healthy patient, right? So this area is for lymphocytes, this dot plot is for granulocytes, this is for monocytes, right? So each of these particles you get this particular type of dots, right, density plot. So in the case of leukemia, for example, then you don't get a particular region. For example, there is no granulocytes over here, there is very less amount of monocytes, for example, right? So so based upon the dimension of the particles, you can actually get this kind of plot, and then you can back calculate and try to understand. You can do some kind of a clinical diagnosis out of it, right? So this is where this particular application of scattering theory has been currently used, that is, which is also known as flow cytometry. Okay. So here I'm just trying to showcase you that this is the granulocytes, monocytes, lymphocytes. So here it's kind of significant. What you can see is for granulocytes, but here there's nothing over here, right? So this is how you can actually perform a clinical diagnosis. Okay, so that's what I wanted to cover for today in this session. In the next session, we'll talk about how we actually find this scattering phase function. How do we get to this scattering efficiency for Rayleigh scattering? So how did we find the sigma s? And then we also find sigma s using the Bessel's function, and and how do we finally can solve scattering phase function using Combs multiphysics as well. Okay, thank you.